Hey everyone, welcome back to another video with Cam Room 5. So we were studying experimental chemistry. In today's video, we're going to be talking about some chemical apparatus and we're going to see where we use them and why we use them. So today's video is going to be about chemical apparatus and their uses. The first one we have over here is a burette. So a burette is a very long tube-like structure and it's used to transfer aqueous solutions. You're not gonna contain it, you're gonna be transferring it for a reaction like acids, like alkalis, especially in titration where we find the concentration of unknown chemical substances. The least count for a burette is 0.1 centimeter cube, which means you can measure a value with certainty to up to 0.1 centimeter cube. Below this level of certainty, you can't measure with much clarity. So the values can be measured up to 0.05, but the value with certainty is going to be measured till 0.1 centimeter cube. The error is 0.05. So when we divide the least count by 2, we get the value of the error. So the error could be 0.05 centimeter cube. Now when we talk about burette, which has an error of 0.05 centimeter cube, we code the values like this: 11.05, 21.30, again centimeter cube, 39.15 centimeter cube. So these are two decimal places after burette, and we make sure that when we are measuring using a burette, we add two decimal places. It starts at 0.00 and ends at 50.00. So these are the values. When we open the knob, the liquid is transferred and we measure the initial and the final values. The other piece of apparatus is a pipette and something else that we have with us. A pipette, or you can call it the volumetric pipette, we have over here is again used to transfer solution, and with the volumetric pipette we have a pipette filler or a safety bulb. Now why do we have a safety bulb? We'll see very quickly. A volumetric pipette has only a very specific value written on top of it, which with around a ring on it. So the ring tells us that up to what exact value we should be filling it. For example, if the pipette is for 25.0 centimeter cube or 10.0 centimeter cube, this is the very specific volume that the pipette measures. You can't measure up to your own wish. So it transfers the solution from one container to the other, but a very fixed volume, like 25.0 or 10.0. Like there are multiple kinds of pipettes, each with a specific value. You fit the safety bulb creates a suction, and then the liquid is drawn into the pipette up to the point, up to the ring where you should be measured it, and when you measure it, you transfer it later. We have two more pieces of apparatus with us. One is conical flask, and on the right of the screen you can see a beaker. A conical flask is not used to transfer volumes, it is used to contain volumes. So we perform the reactions or the titrations in a conical flask. We contain the acid or the alkali over here, but we don't transfer it. A beaker is also used for collection, and beaker is used for the collection of approximate volumes. It does not have a very good level of accuracy over here. So it is like randomly 20, randomly approximately 50 centimeter cube, approximately 100 centimeter cube, but not accurate. Three more pieces of apparatus we have over here include a test tube on the left of the screen. We have measuring cylinder and a gas jar. A test tube is used for qualitative analysis. If you remember the last video, it was used for qualitative analysis. We have the acid or the salt over here and then we test it. A measuring cylinder is also used for transferring the solution. It collects and then later transfers the solution, but it does not have a very good level of accuracy as good as a burette or a pipette. So it measures to nearest 1 centimeter cube, not 0.1 centimeter cube. So it measures values like 11 or 12 or 13, but not with decimal places. A gas jar looks like a measuring cylinder, but it's not. It's very wider, it's very broader, and it's used for collection of gases based on upward delivery or downward delivery. They are very different. Measuring cylinder and gas jar are very, very different. Gas jar doesn't have any graduation on it. You will often see delivery tubes around gas jars because delivery tubes allow the movement of gases into the gas jar depending on upward delivery or downward delivery or whatever the kind of method we are using. So delivery tubes help in the movement of the gases, and the gases are collected in the gas jar, which does not have any graduation on it. Let's talk about a very simple kind of experiment where we design an experiment, let's say, to measure the rate of reaction. Before we go into the detail of the chemical apparatus and their setup, let's imagine that we have hydrochloric acid reacting with calcium carbonate. It produces calcium chloride, water, carbon dioxide. The hydrochloric acid was in aqueous state, calcium carbonate was solid, then aqueous calcium chloride solution is made in water and carbon dioxide is a gas. What is rate of reaction? Rate of reaction means speed of reaction, which means how fast the products are made, how fast the reactants are used up. So it is the change per unit time, and over here it is the change in the concentration of the reactants or the products. How do we measure this change? Over here we have a conical flask which has been set on an electronic mass balance, and there are some other things in the pieces of apparatus over here. On an electronic mass balance, which is going to be measuring the value of mass of the system, you have a conical flask. In the conical flask you can see calcium carbonate and a test tube over here. You have a piece of cotton swab on the top of the conical flask. Inside the conical flask you can see a test tube which has been filled with dilute hydrochloric acid. There's a thread which is attached to the mouth of the test tube. The white powder is calcium carbonate solid over here. The test tube has been attached with a thread so that you can just pull the thread and allow the insertion of the dilute hydrochloric acid immediately into the flask, and when the acid comes in contact with the calcium carbonate, bubbles or fizzing of carbon dioxide gas will be seen. So carbon dioxide gas will start escaping. The cotton swab cannot stop the carbon dioxide gas, remember that. So carbon dioxide molecules escape and the mass decreases because the carbon dioxide is escaping. So the mass keeps on decreasing. It started at a higher value, but then since carbon dioxide keeps on escaping, the mass decreases and later it becomes constant. The mass decreases because the carbon dioxide keeps on escaping, but then it doesn't become zero because there are some other pieces still on the top. The cotton swab just makes sure that the acid does not splash back and there is no evaporation while the system is working. But it does not stop the carbon dioxide, remember that. We have a stopwatch around the whole piece of apparatus so that the stopwatch is going to help us measure the time. So we can measure the mass after every 1 minute or 2 minute or 3 minute interval depending on our apparatus. Now imagine we have a graph. We have time on the x-axis and we have mass on the y-axis. The mass decreases. Initially the mass was really high because everything was on the mass balance, but later the mass decreases as soon as the reaction begins because carbon dioxide molecules keep on escaping from the system. Finally, the mass does not become zero, but it becomes a non-zero value. When the mass becomes constant, it shows us the mass of the flask, the remaining solution, which includes the remaining calcium chloride solution, the remaining water, it shows us the mass of the cotton swab, everything that's on the flask. So that is why it's not becoming zero. But then it becomes constant because after a while the reaction stops. So no more carbon dioxide is more escaping. So this kind of apparatus shows us how we can arrange all different kinds of chemical pieces of apparatus to have a measurement experiment for the rate of reaction. We can measure the mass after equal intervals of time. So that gives us the rate of reaction in gram per second. And then we can convert the grams into moles, because mass divided by molecular mass becomes moles. So it also helps us to calculate the moles per unit second. I hope this idea is clear to us, and the next video we'll try some more experiments. Stay tuned, guys. Thanks.